We're going to get started. So good morning, afternoon, evening, wherever you are. Thank you so much for joining us virtually. We appreciate you all staying safe while we still get to share our networks and learn some things. So the first thing I'd like to do is recognize that even though you may not be on campus, our campus and my home are on the unceded ancestral territories of the Coast Salish people, the Squamish, the Musqueam, and the Tsleil-Waututh. And we are, even on an ugly day like today, I know that I'm quite happy to be on these lands. So it's always important to remember that. So we're extremely lucky today to have Dr. Lino Coria coming to speak to you all today about real-time object detection for mobile applications. So I've seen Dr. Coria's talks, and I'm just so glad that he accepted my invitation to come in, because he is an engineer, an educator, and a researcher in computer vision. And so he has a master's degree from McMaster University and a PhD from University of British Columbia, with over 15 years of experience working in both academia and industry. For over 6 years, he was a full-time professor at ITESO, I don't know how you say that, in Guadalajara, Mexico. And he's taught several courses at both undergraduate and graduate levels at UBC and Langara. So as an engineer, Lino has developed machine learning solutions that work in multiple environments. And this experience has allowed him to understand the challenges of machine learning in production. So currently he's working as a computer vision engineer at, I also don't know how to say your company's name. Is it Ecoation?
Ecoation, yeah.
Ecoation Innovative Solutions. So I'm really excited to hear, because as several people know, my background's machine learning, but not nearly as applied as yours. So looking forward to it. Thank you so much for being here.
Thank you so much, Bethany, for having me here. And thank you, everybody. I understand that it's pretty late for some of you, or pretty early. And I appreciate you taking the time. So I'm going to share my screen. Oh, okay, there it is. Okay, great. Okay, so I'm going to talk about real-time object detection for mobile applications. And my name is Lino Coria. Now, preparing this talk was challenging because I was trying to make a talk that is useful, interesting to everybody. And I understand people come from different backgrounds. So if some of the material I'm presenting is too basic, I would say just be patient, and something interesting hopefully will happen soon. So I created this outline. I want to talk a little bit about cameras being everywhere, and a little bit about computer vision, what we understand for computer vision, or what I will talk about. And then some of the traditional computer vision techniques very quickly. Then we will move to deep learning techniques that are I guess, the most successful techniques that we have right now. In particular, we have, for computer vision, we have convolutional neural networks. I'll talk quickly about what they are, and then how we can train them for object detection, and how we can adapt these models that we have trained to work on mobile devices. So this is essentially what I want to cover today. And of course, there will be opportunity for questions. And if someone is watching this not in real time, but they're watching a recorded version, my Twitter handle is Lino Coria, just as my name. And you can contact me, or just search my name and contact me any LinkedIn or whatever. And I'm happy to reply to any questions you might have. So cameras are everywhere. The first picture on the top left shows something that I shot while I was a postdoc at UBC. And this is me playing with a rope. It's a 3D camera. So it's recording a left channel and a right channel, right? And it allows us to estimate depth and, well, and do silly things like me with the rope here. The picture you see at the center, this was taken a week ago, and this is me visiting a greenhouse in Delta, British Columbia. We are doing a lot of changes to my job right now is using computer vision to count and classify fruit. So for instance, you have tomatoes there, and you can see some tomatoes are red and some tomatoes are turning, and some are pink, some are green. And I have a 360 camera there because we are now going to start using these cameras in the greenhouse. And so these are there's all these different kinds of cameras. I wish I was a teenager right now, like when I was a kid and I was like looking for these cameras, and now they're everywhere. There's obviously security cameras that might not be like a happy a happy thing, but they are there. And of course, our phones have a lot of cameras, and I wanted you to think how many cameras can you identify in your room. My phone has, to my knowledge, it has 2 cameras, but there's probably more cameras everywhere. Some people have them in their doors, right? Like as people ring the door, that they can see it. I have my DSLR. So we have cameras everywhere. And this is why computer applications are everywhere, and especially on our phones. By computer vision, there's tons of applications. People immediately think about self-driving cars. That's like the ultimate application that a lot of people can think of. Another application is face recognition, which is, there's face detection, which is essentially detecting that there's a face, but there is face recognition, which is saying, oh, based on features, based on, say, the distance between my eyes and the relationship between my eyes and my mouth and this and that, it's saying, oh, this is Lino's face, right? From this picture, right? And this is what I guess Facebook does, or Google does, when you upload your picture and say, this is you, this is, this is John, this is Peter. But what I want to talk about is the thing we have at the center. We have objects, and we can detect them. We know where they are, and we know what objects they are. Now, when it comes to computer vision on mobile devices, there are 2 kinds. Sometimes these are my daughters, and they are playing with, they love using filters. They, seeing how their faces turn into something else. And usually for these filters, they have to be connected to the internet. So they need Wi-Fi. And this is not running in their phone. This is running somewhere in the cloud. But there are other applications where you want everything to run on the phone. Why? Because it's cheaper, right? Like you don't have to, if you're a small startup and you don't want to be paying for services of running all these neural networks in the cloud, you want them running on the device. And so then you have some constraints. You have running time. You don't want this to take forever, right? You want to quickly identify objects, for instance, and you don't want this to have like memory issues and involve a lot of computations. So we're going to see that when you're working with neural networks require a lot of computations, right? So they are very effective, but they are computationally intensive. And so you want to put that on a phone. So how can we have this state-of-the-art technology that requires a lot of computations? How can we have it on a mobile device? And speaking of my daughters, this time for me between 2 and 3 is when my daughters come back from school. I'm hoping there's no noise, but I just apologize if my dog starts barking or something like that happens. The girls have been instructed, but let's see what happens. So anyways, these are like the basic computer vision problems that we have. Classification is, you see, let's say you want to identify cats, right? You see a picture of a cat and you say, and the computer vision algorithm says, oh, there's a cat in this picture. You don't know exactly where that cat is, but you know that there is a cat. Now, the 2 in the center, I would call both of them object detection. This graph somehow calls it classification and localization, the first one, because it's a single object, but I would call both of them object detection. And this is not only is there a cat and a dog and a duck, but I'm telling you where they are. And then even farther is instant segmentation. And this is telling you where every pixel that belongs to a dog and every pixel that belongs to a cat, right? So you can isolate this from the rest of the image. If you, like, I have a Pixel phone and I take pictures, and then it has this option of color pop-up, which means that the person remains in color, but the background goes black and white. It's essentially this segmentation techniques that are being used. But I'm going to talk about about object detection and putting it on your phone. And this is the one thing that I've done before, and I thought it's it's a cool application, fun application. So this is what I will be talking about now. First, but yes, I said I'm going to work on object detection, but I'm going to start explaining classification, because classification is the most basic problem. It's the easiest to understand, and then from that we can expand and talk a little about object detection. So there's a lot of traditional image classification techniques. Essentially, what you want to do is to find features in an image, right? Let's say we want to classify churches. We want to understand a church, and there's these common things that are present in churches. We cannot write an algorithm really to describe what makes a church, or what makes an old building, or what makes a cat, right? This is very complicated to write logic about that. So the older techniques, what they would do is to find features. Features are small, interesting sections in images, usually corners, usually edges, right? And you say, this is interesting, this is interesting. And you find these features and you say, every time you find these features, this is a cat. Every time you find these features, this is a dog. But you need to spend a lot of time, and you need to be very good at it. You need to be very good at finding these features, identifying which are the important ones, and to use them. So this is the, I would say, old school way to do image classification, which is the from the two diagrams is the one on the top, right? It requires a lot of human effort and a lot of being smart about it, trial and error. Now, neural networks make our life easy, but make us a little lazy. And what happens is that neural networks do not only classify images into, this is the image of a cat, this is the image of a dog, but they also find the features themselves. So this is great. Like, we don't have to worry about it. We have an image as our input. It goes through a neural network. And then at the end, we get a classification. And the neural network figures out how to find the features. What are the best features that we need? So this is why deep learning has become very successful. This is why so many of the current algorithms that we have for just recognizing our speech, right? For translation, for many things, computer vision are based on deep learning. Now, something that I find useful is, well, because a lot of people might be confused. Sometimes when people are talking about deep learning, they call it AI. And they use AI as a synonym of deep learning. And I just want to show this, and you probably might disagree with this this thing, but deep learning is part. So artificial intelligence, let's start like this. Artificial intelligence is basically having machines making decisions that are kind of human-like, let's say. Not everything is machine learning. There's other ways to do it, but most of the time when we're talking about artificial intelligence, we mean machine learning. And there's lots of techniques, let's say old school machine learning techniques, that I would I think I read your program, and you're covering all of them. So I think this is great, because I think that a lot of people that get into deep learning have never learned the, let's say, the classic machine learning approaches, which are very important. And sometimes you don't need deep learning, right? You can just think of good old machine learning technique, and this works. And then we have within machine learning, as I said, there's this old school algorithm, but then you have neural networks. And neural networks can have many layers. It's a bunch of computations. It's layer after layer of computations. When you have a lot of layers, then people call it deep learning. So I just wanted to show you this, to say, yes, what we are going to be showing here is AI. In particular, it is deep learning. And in particular, it's going to be based on computer vision applications. So this essentially, this is what we want. We want to have the picture of a cat, and we want the neural network to extract first some basic features, and then with these features to construct more other features that are more particular to the cat, right? So the first features are going to be very general features, and this is like a super simplification of what a neural network is doing. But in a sense, it is finding these areas of interest, these edges, these corners, these weird shapes, and then it's putting them together and identifying. Every time I find these things, it means that this is a cat, right? So this is what we're trying to do. There's a particular type of neural network that is used for computer vision, and this is called the convolutional neural network. And it has, let's call it 3 steps. The first step is to have your input, right? If we can call it a step, you need to have an input, which is an image. And then it goes through the stage where the features are learned. Remember, features are these interesting sections of an image. And then once you have these features, you have to classify them. You have a final stage where is, now that I have all these features, I need to classify them and decide if I have a car or a truck or a van or a bicycle here, and what are the probabilities that we have. Now, I'm not going to go into detail with these neural networks. And usually if you're just working as an engineer, not as a researcher, but as an engineer, you need to it's good to have a good understanding of these stages, but probably you don't need to know all the details. But anyways, I would still, of course, strongly recommend that you go and you read some books and some papers, and especially some websites. Some people spend a lot of time making these really cool graphics and demos and some tutorials with code and things like that. So this is this is probably very basic, but I still decided that I wanted to put this slide here because maybe some of you might be familiar with machine learning, but haven't really worked with images. An image that you have, a picture that you have, is actually has 3 channels. Has the red, the green, and the blue channel. So it's in RGB color space. And essentially each one of the pixels that we see has has 8 bits that represent red, values from 0 to 255. Then another value that represents the amount of green, and another value that represents the amount of blue. The more red there is in an image, the wider it looks here. So if you look at this region here, you can see that the apples, for instance, they're very white here when it comes to red, right? Because there's more information about the red channel. But then other things like this section, which is blue, we don't have anything here. We don't have anything here, but here we have a lot of it, right? So an image is actually 3 channels: the red, the green, and the blue. And this is our input. We usually process the red, then we process the green, then we process the blue. Then let me go back to this. So then once you have your input image, it goes through this feature learning stage that has a convolution section and a pooling section. The convolution layer, basically what you have is a set of filters. And these filters can be, for instance, if it's a high pass filter, it only lets, it detects like big changes, like for instance, edges or corners or things like that. There can be all sorts of filters, and these filters go through the image, but it's the same filter applied to small regions of the entire image. And the reason you want to have the same small filter going throughout the whole image is because regardless of the position of the cat, let's say you want to detect a cat, it doesn't matter if the cat is in the bottom right corner of the frame or in the top left corner of the frame, it's still a cat. So you want to make this shift invariant. So it doesn't matter where the cat is, we will still find that cat. So that's why we have the small filters that go through the entire image. Of course, a color image has 3 channels, and then you have a bunch of filters being applied to this image. You create a lot of data. You create a lot of values that are no longer pixels, because now there's not really a one-to-one representation. And so then the more elements your neural network has, the more computations you need to do, and the more prohibitive these computations become, right, as this goes along. So then there's this, every convolution layer is followed by a pooling layer. The pooling layer, essentially what it does, it sort of summarizes the convolution layer. It takes away most of them. Let's say 75% of the values disappear, and the pooling layer, it's a simplification of it. Usually what you get is you get a group of values and you pick the largest one. This is called max pooling. The other option is you get the average of this value. Most people use max pooling. I think it's more effective to do so. So anyways, you do these convolutions, you create all these edges, all these features, then you just take a few of those and make it smaller, and then you apply this again, and then you get features from these features, and you keep doing that. And this is just like a basic structure. There's many proposals on how to do it. And so this is just to learn the features, to extract features. And finally, you have your classification section. So again, maybe this diagram is a little bit more useful. And I think this is what you need to take from this all convolutional neural network conversation that I've been having here. You have an input, which is an image. Then it goes through a convolutional base, which is feature extraction, understanding what's unique about the image. And then you have your classifier. And this is, if you've done some deep learning for other types of applications, this is your, like a regular classifier. We have these images, these volumes that we have, these 3-dimensional spaces, we flatten them into just 1 dimension. And then it goes into like a regular neural network. And you come up with a prediction. So I know that I have talked a lot about this convolutional neural network. I'm hoping that it took me a while to understand them. It took me a while to figure them out. And even now, as I was preparing, there were a lot of questions that I had, like, why do we do this? Why do we do that? So don't worry about understanding this perfectly. What you should just, I would say, worry about is understanding that you have an input, then it goes through a convolutional base that detects the features regardless of the location of the object. The cat can be anywhere in the image, and we're going to extract those features because we're using this convolution, these filters. And then we have a classifier. We classify these images, and we have a prediction based on these features. There's 80% chance this is a dog or this is a cat. This is, I guess, the main takeaway. Now, object detection is an extra step. We don't only know that there's a banana in this picture, but we know where it is, and we have the probability that this is a banana. So for an object detection algorithm, your input is your RGB image, your red, green, and blue image. And then your output is a list of the bounding boxes. The bounding boxes are these rectangles that surround the object, right? And then you have a class label. So there's one for an apple, and there's one for a banana. And then finally, a confidence score. We're 79% certain that this is an apple, and we're 80% certain that this is a banana, right? And so this is what you want for object detection. Now, if you understood classification, and now you had the challenge of, okay, I have classified, I know there's an apple, and I know there's a banana, but how do I know where they are exactly? So what people do is they have this different scaling of an image. You have your image and you scale it in different sizes, smaller sizes, and you have a window of a fixed size that just goes sliding. And as you slide it through the image, let's say first the largest image, every time you find, let's say in this case, a tomato, you say, okay, here's a tomato, right? And then this might be too close, right? The size of your window might be too close to identify that this is a tomato, but no worries. You have in your pyramid, your image pyramid, you have a smaller image and you keep the sliding window the same size. So now you capture a full tomato and you say, oh, here's a tomato. So by scaling your picture and running a sliding window through the picture, you can identify not only that there's a tomato, but where is the tomato, right? Now I have simplified this, and of course you can see that this is computationally intensive, right? Sliding a window and having the same image in multiple resolutions, it is time consuming. And there are smart ways to do this. And you can find lots of object detection algorithms out there that use these ideas. This is the basis, but they use these ideas in smart ways, right? So you will find that there's the SSD algorithm. It's then you have the RCNN, and then faster RCNN, and all this algorithm. I won't go into this. I just want to say SSD is one of the fastest ones, and it's one of the ones that I would recommend to have on your phone, but I'll talk a little bit more about that later. And you can see that a lot of this use a data set called COCO. So they have been trained with a data set called COCO. COCO is Common Objects in Context. And this is a data set that is used for detection and to find key points. So not only detect the bounding box, but also find these points, let's say where my eyes are, where my nose is, and all these other things, poses and things like that. And a lot of people use it to train, right? Because it's very easy. You just go and download it and you train your neural networks with it. And it has become a benchmark. A lot of people, COCO, and there's other data sets that are used as a reference, right? Like if I want to prove that my new method for doing object detection is better than the previous ones, I have to have a common data set to make these comparisons. So people have been working with COCO and with a few other data sets to make comparisons. Now, here's the interesting part, or this is the part that I would say nobody talks about a lot, but we should talk more about, and it's creating your own data set. A lot of people want to try neural networks and want to play with computer vision applications, and they just download a data set, and it's cool. I think it's a great way to start. But if you want to work on a very unique project, you need your own data set. Sometimes there's data sets already for things that everybody uses. So if you look for a data set of faces, you can find many, right? If you're looking for people, you can find it. If you want to bicycles, cars, airplanes, dogs and cats, you can find them. But sometimes you want something really unique. And this has been the case of my last two jobs. In my previous job, we were creating custom footwear. So we needed to identify your foot, and we needed to find key points in your foot. And the way we needed the pictures of your feet, we could just not go and search them, right? We needed to collect this data set. And maybe you want to identify something like in the case of the tomatoes, it's not just regular tomatoes we want to find, but this particular tomatoes that we have on greenhouses. So you go and you collect your data set. Now, I'm saying here it's a big responsibility. And you might think, why is it a big responsibility to get a data set of tomatoes, right? Tomatoes are just tomatoes. Like, what's the big deal on what's your ethical responsibility on finding it? But I'm talking that if my model is not finding these tomatoes correctly, it's going to impact the decision of the growers, because they are saying we have this many tomatoes. So we are expecting, let's say 70% of our tomatoes are green. are green and the other ones are red or turning. So we expect that within a week, this is going to happen, right? So a lot of decisions are going to happen based on my model. And I will just share a little story. I'll ask a question. Do you know that there's black tomatoes? I did not know that. And I've never seen one in real life. I just know that there's a greenhouse in France that has black tomatoes. And so this is the responsibility, right? You have to do your research. You have to think what kind of, am I missing something? And this sounds like a beautiful analogy of things that happen in life. I'm having diversity and cultural differences because I think this happened to, I think it was Google maybe, where they would have, every time you would type wedding, the neural network learned to find a woman with a white dress, right? But not every culture has a wedding where the woman has to wear the man wears a tuxedo and the woman wears a white dress. This is the way we're used to seeing it, right? And this, the weddings I've attended, but the world is bigger than my little bubble, right? So this is why you have to be very careful, especially, when it involves people. And I would say everything involves people, even my tomatoes involve people. And you have to think, who is this going to be helping this group? Like let's say I'm creating an app and I need to collect pictures of dogs. Is this going to be helping dogs or is it going to be harming dogs? Like, what is the use of that, right? And I know this is not a talk about the ethics of AI, but I also know that it's something that we should all care about. Long time ago, I went to this, I was talking to this engineer who was doing classifying pictures of people into ethnicity. And I asked him, what would his algorithm, how would it classify me? And he didn't know. And probably because there were no people like me in that database, right? He told me he had 4 categories. So he was dividing every person into 4 ethnic groups. And he didn't know how to classify me there. And it's the first time probably he had this question asked. So anyways, when you create your data set, try to think about edge cases. Try to think, am I featuring all the dogs that I can feature? Are they all the sizes? How about dogs that are missing a leg? How about old dogs and young dogs and, all these things? And dogs are just an analogy of the many, many classes that you can find. Now, I searched for many ways. So I encourage you to do this as an exercise, that you create your own data set. You collect all the images and then you label them. This is free open source software called CVAT, computer vision something. I forget what it means, but you use this to annotate your images, right? So this is a picture where you just draw your bounding boxes and you label them. And I would suggest that you do this. You do this as an exercise because you're going to learn a lot by creating your own data set. Now, every data set, it's not just data that you're going to use for training. You're going to have, sometimes people only use training and validation, but I would suggest that you have a training data set, a validation data set, and a testing data set. And maybe this is very basic to you, and I apologize if this is too basic, but I'm going to explain what each one of these tests is. Now, training is the largest of the data sets. Some people, if you search, people are going to recommend that about 70% of your, let's say your images, let's say you have 1,000 images, right? So about 700 of those images, 70%, you're going to use for training. So the neural network is going to use them as inputs and is going to learn to classify them. And then every now and then you bring your validation set, right? This validation set is, let's say, 15% of the image. So if you had 1,000 images, you have about 150 images here that you're going to use for validation. And you make them go through the neural network, through the convolutional neural network as it is learning. And you're going to see the score of how good it is at classifying, right? And ideally, you want your training and your validation sets to behave the same. So as you keep training, it's getting better at classifying the classes that you're showing it. But then when you use your validation set, you still want it to get better at classifying the validation data set, right? If it becomes really good at detecting the classes, at classifying the training data, but not the validation data, it means that you are overfitting, which means that you have shown it so many you have shown it a limited number of examples that now it only understands those examples, right? Like if I only show 5 pictures of a dog, and then I bring a new dog and doesn't know that this is a dog because it just learned this very specific features of these images that I'm showing it. So you want it to be able to work both on the training and the validation data set. But then the first time you train a neural network, you're not going to get it right. And you say, you know what, I'm going to change these parameters. And you keep changing and you keep running your training and your validation until everything looks perfect. But maybe you were just tweaking so your validation looked as good as your training. And that's why you need a testing data set that you bring at the very end. And at the very end, you bring it, and then you hope that this behavior, the accuracy in classification is as good as in the training set and the validation set. And this, I think, is where you need to spend a lot of your time. A lot of people actually, they just do reruns and change parameters. But I think that if you carefully build your data set, if you build it carefully, that you make sure that you're building it yourself, you make sure that you have all these edge cases and this and that. This is probably more important than making all these calls about tweaking this parameter by 0.001 and things like that. It's also important. I'm not saying it's not, but these are very important things to keep in mind as you continue. Now, when this is transfer learning is a technique that you can use anytime, but especially when you don't have a lot of data. You created your data set, but you don't have, let's say, 100,000 images. You only have like 2,000 or 3,000 images. If you remember when we discussed convolutional neural networks, we said that there were two sections: the convolutional base, which is feature extraction, and then the classifier. So now there's all these available neural networks that you can download for free, right? Google has them, Facebook has them, and you can just download them, and they have already been trained to find, let's say, cars and bicycles and boats, or people and cats and dogs, but you want them to identify, let's say, pencils or something unique that is not part of that database. Well, one strategy is to start training from scratch, right? Like all the blue stuff is what you have to train. You retrain the feature extraction process and you retrain the prediction. But also, if you remember that picture with the cat and the edges, and then the first layers of a neural network are going to be very basic shapes that usually apply to everything we have seen in real life. So you can freeze them. Freezing means you're not going to change those values, and you only train, let's say, half the layers, the last layers of your feature extractor, and then you just train your classifier. Or, and this usually works very, very well, you don't worry about the feature extraction process. You freeze it, you don't change it, and you only train the classifier. And usually this works very well. In a very short time, you have a very good classifier, and you can use it for your stuff. And this I have used, right? I have used, for instance, in my current job, we already had a nice model for tomatoes, and now I wanted to create one for finding peppers. Tomatoes and peppers are relatively similar, so I didn't have to retrain everything, right? I just had to train a little bit, and then boom, very quickly I had a very good pepper model, right? So But if you're using real life images, if you're using things from, from the world, it's very easy that transfer learning is going to solve your problem. Now, the other thing you can do is data augmentation. These are flowers, tulips. I'm reading. I'm pretty bad at flowers, but I just read that these are tulips. And the images that you see on the right, you can see as essentially the same picture, right? Of that you see on the left. For a human, they are essentially the same picture, but for a computer, it's just a bunch of different numbers, right? But with the same image, we make small tweaks. We rotate it, we crop it a little bit, we scale it, we change the brightness, and we're creating extra data, right? So data augmentation, it's a great tool to increase your data set. Now, you only do this on the training set, because this is the set that you want to expand. But your validation and your testing set, there's no need to do that, because you just want to make sure that real life images, you're still being able to make detection correctly. But anyways, these are just little tricks that you can do. Transfer learning and data augmentation to have a small data set, a relatively small data set, become a larger data set. Every time I tell people about training and I say we need a large data set, they say, how large, right? And it's horrible to give absolute values to tell people, oh, you just need this amount. But my experience shows that for real life objects, if I have 2,000 images, it's pretty good, right? I am not comfortable with that number. Don't quote me. I guess you can quote me on that, but I'm not saying that's the truth always. But I would say starting with 2,000 images, it's a comfortable number based on my experience. Now, I'm going to talk about how to put it on your phone, right? Like this is a long computation intensive neural network, how to put it on your phone. Now, I'm going to talk about TensorFlow. TensorFlow, it's a framework from Google for running neural networks. And I'm going to use TensorFlow as an example because it's the one I use, but it's not the only one available. Actually, we got this is my previous company, and we are using it, as I said, to create custom footwear. We got a shout out from them on how we use TensorFlow to create this custom footwear. And in particular, we use something, a tool that they have, which is called TensorFlow Lite. And what TensorFlow Lite does is it gets a big neural network that you train in the cloud. And so through some clever process, like for instance, instead of using float, they use integer values and things like that. They managed to make it a very small, not small in terms of layers, still the same amount of layers, but less computations and smaller in size, right? And so you just transform it with their tools into TensorFlow Lite model, and then it's something that you can put on the phone. And I got to be at the last year when people could still go to conferences. I went to the Google headquarters, and my tweet was featured there as like a cool application of using TensorFlow Lite to have this on a mobile device. And you can just go Google TensorFlow, and you can Google and search how TensorFlow Lite works. They have a really nice demo of something already trained, right? So this is how you can start. You just grab a model that has been trained, and then you shrink it using their tool for TensorFlow Lite. And then it becomes like an object detection is like 4 megabytes, the model that you end up with, and you can put it on your phone. Now, I'm not an expert on mobile devices. I usually build the model, I make it small, and then I give it to a great mobile developer. And this is as far as I can get. But if you know how to create apps, it's very cool that you can use great AI, right? That you train somewhere else, and then you put it on a phone. And you can do it for Android, and you can do it for iOS. And I'm using TensorFlow, as I said, because that's the one that I know. But for instance, PyTorch also has PyTorch Mobile, right? So you train your neural network, and then you go to you use the tools. PyTorch is a different framework. This belongs to Facebook. and they will make sure that they use smart computations and everything to make it small so that it fits on your phone. So just to summarize, these are the steps. You have to build your data sets, a training, a validation, and a testing data set for the object that you want to detect. You have to draw the bounding boxes in all these images. Listen to some good music, a podcast. This is boring. It's a tedious process, but I recommend you do it. I mean, some people obviously hire some companies, usually overseas, to do the labeling. But I would say as an exercise, do it. You learn a lot by doing it. And then you pick the right model. There's a lot of models out there for object detection. Look at the size, look at the performance. Some of them might work better for big objects. Some of them might work better for small objects. And then you train on your computer if you have a GPU. I don't, so I usually have to train, well, a computer that is far away. I use it, right? Or you can do this in the cloud. And I would say don't start from scratch. Use transfer learning, data augmentation, right? To create a better model. And then use one of these tools available to convert it into a light model. And then you can deploy it to a mobile app. So anyways, this is very quickly my experience on how to do object detection on a mobile device. So if you have any questions or comments, I'm happy to answer them.
Thank you so much. Are you able to see the chat, or would you like me to read you the question?
Oh, I don't see it. Let me, oh, here, I can see it now. Okay. So the first question is, do you use the RGB color space because it separates red and green tomatoes in separate channels? Did you try other color spaces? So this is a very good question. And some of it I probably won't be able to answer because it might be like a trade secret. So the RGB is not from me. The RGB is how, I guess, every image is usually in RGB, right? Like the way we have our images is in the RGB color space. And we use that for training. And to be honest, we didn't experiment with other color spaces. We could, but we just went through the regular RGB and we're training. But people used the RGB color space essentially for everything. Now, I do have to classify fruit. I have to classify fruit into red and green and turning and pink, for instance, for the tomatoes. And then I would say the RGB color space is not the best color space. So for that classification, we actually use old school computer vision. You don't have to use deep learning for everything. So we got smart and we found better other color spaces that can help us do this better. Now, the second question, how do you balance between improving performance on the computer vision model and developing processing responding time as a mobile app product? So, so you essentially have to decide, what is it that I want? Do I want this to be super fast? Or do I want this to be super accurate? And usually you cannot have both. And then I guess the way you have to think is, it all depends. For instance, the app that we were doing, right? People were taking pictures with their phone and we had to detect their feet. But the problem is that some people had like the latest phone and some people had like a phone they bought like 5 years ago. And it had to work. We at least we needed it to work with. We cannot assume people are going to have the latest phone available, right? We still want them to be our customers, I guess. So you have to make a decision. So that's why I said the single shot detection SSD algorithm for object detection. It's a fast one and it's really good. So I would say that I see a lot of tutorials, a lot of demos recommending that one, right? So so you have to think about that, and you can always there's the other options that the layers, you can use less layers, right? And then it's a smaller neural network, but it becomes less accurate. So these are definitely the things that you as an engineer, you need to discuss. And sometimes it's not just your call, right? Like, as I said, I was not designing the mobile apps. And I know I can read it and I can sort of understand what's happening. But if I'm asked to build a mobile app, I would probably cry. So I had very, very experienced colleagues, very friendly. So I would have conversations with them. You talk to the whole team about what size is allowed and what speed is desired, and based on that, right, you have to build something. Now it's very important that you you use everything you have, all the tools that you have to create with the best structure, still create the best model. So I'm hoping I've answered that correctly. And then another question, is it becoming more common to use GANs for creating more data alongside the data augmentation task you discussed earlier? So, so these are neural networks that with, I guess, very little information, they create, they're able to create synthetic objects. So the most famous ones are the ones where you have faces, right? Sometimes you give them like a little input, or sometimes, and then they create this nice face out of let's say a few pixels, right? And a lot of people are using it, I guess, to create synthetic data. I would say for the applications that I'm trying to do, we talked, for instance, we had this conversation about how about we have all these pictures of tomatoes and we just put them everywhere, right? Once you have a synthetic picture of a tomato, you can tweak it a little bit, you can make it a little longer, you can change the color a little bit, and then you can put them everywhere. You can make combinations of all these tomatoes, in different images. And I guess you can do that. And I also think you can create them artificially. And I think that's fair, and I would say use it. And this might be just our bias, but we try to go to the greenhouse and we try to get our own video, and we try to use it so that we're certain that this looks like a real solution. I was actually, before this talk, I was reading some article about, and this is back to all the problems that there are when there's no diversity, and all the, I don't want to call them mistakes, but all the generalizations that come from using GANs, right? Like all this, if you feed it, if you say men look like this, women look like this, and this is what they learn, you might get some results that you don't like. So you could bring bias with GANs, I would say. But sure, you can use every tool. I think that's valid. Now the benchmarks like Coco use MAP, which is mean average precision, as a performance metric. Does this work well enough in practical applications as well, or do you need other metrics? This is a good question. We use, because everybody uses this mean average precision, and without going into details, it's just telling you from the ground truth, whereas the bounding box drawn by a human and the bounding box detected by your algorithm, are they overlapping? And essentially, it's a measure of the false positives and the false negatives that you get, and it's what everybody's using. And some people might have, might have some issues with those metrics. I can tell you that we have, for instance, when we're doing tomatoes, this is a great tool, the mean average precision. But when we're doing other objects where there might be only a couple of them in a frame, let's say you're doing some objects and there's just like 2 of them, instead of like 100 people, there's only 2 people, and you get it wrong, then this looks like your performance is pretty poor. But it not might be that I'm saying a lot and I'm not saying anything. What I want to say is always use your intuition, always look at their numbers and don't think of them just as numbers. Look at, is this metric making sense? And I would say MAP makes sense a lot of the times, but sometimes you might want to find a different way of measuring success. Whatever works for you. Just don't, I would say, don't fool yourself into, because everybody's using this, I should be using it as well.
That's fantastic. Thank you so much. And you see he's posted his Twitter handle, which is fantastic. And Jackie has posted a feedback form in the chat for anybody who would like to let us know. But thank you so much for your time today. And yeah.
Well, thank you for inviting me. I'm very happy to share my experience. I saw that Trevor Noah was recently with you. I know I cannot be as funny as charming as Trevor Noah, but I hope that at least this was a little useful to some of you. Thank you so much.
He didn't go into convolution networks, I'll tell you that.
Okay.